I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on the ideal gas law. In this series of videos, we're going to talk about thermodynamics, an important topic in physics to help understand how engines work. And we're going to start with the ideal gas law and pressure, temperature, and volume and how they are related to each other. So first, we're going to start with some vocabulary. So heat and thermal equilibrium. So heat is defined as an internal energy transfer between objects, and the objects have different temperatures. So that's the key. They have to have different temperatures in order for there to be an energy transfer. And the energy transfer is from a higher energy to a lower energy, or a higher temperature to a lower temperature. Now, thermal equilibrium occurs when two objects are in contact with each other and they have the same temperature. Therefore, there's no energy transfer between them, so there's no heat transfer between them. So objects that have thermal equilibrium, there's no energy transfer. Now we're going to talk about the Zeroth Law of Thermodynamics. So you might be thinking that's kind of a weird name. Well, they came out with the first and second law of thermodynamics and then decided that a basic topic was so important it deserved its own law. So they went before the first and named it the Zeroth Law. So it states that if two objects are in thermal equilibrium with a third object, then the two objects are in thermal equilibrium with each other. So it seems kind of trivial, but what that helps us do is helps us to define temperature. So objects that are in thermal equilibrium have the same temperature, which is why this law was so important and named the Zeroth Law. So we're going to talk about temperature and temperature scales. Temperature is the measure of the average speed of particles in a substance. So all particles aren't moving at the same speed. They just have an average speed, and that average speed dictates the temperature. The faster they're moving, that means the higher the temperature. And the slower they're moving, the slower the temperature. Now there are three scales that were developed. So the Celsius scale is the first one we're going to talk about, and that's the one we're going to use a lot. And this is what's used in most other countries. Then we also have the Fahrenheit scale, which is used in the United States predominantly. And then we also have the Kelvin scale, which is known as the absolute temperature scale. And we'll talk a little bit more about the Kelvin scale and why it's the absolute temperature here in a minute. So Celsius scale was developed based on the boiling point and freezing points of water. So 0 degrees Celsius was the freezing point of fresh water, and 100 degrees Celsius was defined as the boiling point of fresh water, and equal increments of temperature were marked in between 0 and 100. Now, the Kelvin scale, we said, is based on the absolute temperature. What absolute temperature is, it means that matter ceases to move at 0 Kelvin. Matter is constantly moving. The faster it moves, the higher the temperature. But if there is no motion, the temperature is 0 Kelvin. Now, Kelvin and Celsius have a relationship where a change in temperature of 1 Kelvin is equal to 1 degree Celsius. So an equal change. So if I can find the change in Celsius, I know the change in Kelvin. But that doesn't tell me the temperature. The temperature of Kelvin is equal to the temperature of Celsius plus 273.15. And we're just going to go ahead and round that to 273 to make it a little bit simpler. So Celsius plus 273 is going to give us the Kelvin temperature. So the Fahrenheit scale is based on the freezing point of a saturated solution of a salt and water. At that point, it was called 0 degrees Fahrenheit. And roughly based on the temperature of a human's body, which is a little less than 100 degrees Fahrenheit, but that was what was used for the Fahrenheit scale. So equal increments were marked between 0 and 100. So fresh water freezes at 32 degrees Fahrenheit and it boils at 212 degrees Fahrenheit. Celsius and Fahrenheit have a relationship that 1 degree Fahrenheit is equal to a 9/5 or 1.8 degrees Celsius change. And the equation to convert is Fahrenheit is equal to 9/5 times the degree Celsius plus 32. And a little side note is that Celsius and Fahrenheit actually have the same temperature at one distinct temperature, and that's negative 40 degrees. So negative 40 degrees is both Celsius and Fahrenheit, and that's when their temperatures are the same. Now we're also going to talk about thermal expansion. Thermal expansion is a property of matter that matter increases in volume when the temperature increases. So if you think about it, the molecules are moving faster, they need a little bit more space, so it increases the volume as well, as we will see a little bit later on. Now, this is important to know because this is how a thermometer works. As the temperature raises, if you take temperature of boiling water versus cold water, the liquid in an old style thermometer goes up and down, and that's because of thermal expansion. Another important use of thermal expansion is on our roadways. Concrete expands and contracts with higher or lower temperatures. So the higher the temperature of concrete, like in the summertime, it's going to expand, and it also contracts in the wintertime when it's much colder. That's why we have the joints between the concrete blocks on the bridges to allow for that expansion so the bridges and roads don't crack. Now, the way you can calculate thermal expansion is L stands for the length, so that's the change in length or the initial length of L naught on the right side of the equation. Alpha is the coefficient of linear expansion. That's a constant based on the substance, like concrete or steel or specific substances. And change in temperature is the change in temperature in degrees Celsius, but also could be Kelvin because a change of 1 degree Celsius is change 1 Kelvin as well. Now let's get into the ideal gas law. So first off, what is an ideal gas? So it has a large number of gas molecules and they have elastic collisions, meaning that there's no energy that's lost during collisions with the walls of the container or the gas molecules themselves. And there's a large distance between the gas molecules and they exert no forces on each other except during those collisions. There's no preferred position or no preferred direction for the velocity. The gas molecules just move randomly about in the container. And finally, each gas molecule occupies a negligible amount of volume in the container. So basically, no space taken up inside the container. So we say that an ideal gas has zero volume. Now we're going to look at the relationship between pressure, volume, and temperature and the number of gas molecules in an enclosed container. So we're going to look at proportionalities for pressure first. So let's define what pressure is. So what causes a pressure inside of a container is there's collisions with those gas molecules in the sides of the container. And the more frequent the gas molecules collide with the sides of the container, the higher the pressure, and vice versa. The lower the pressure, less collisions. So look at volume and pressure, temperature and pressure, and number of molecules and pressure. And so when we look at volume and pressure, that's assuming that temperature and number of molecules remains constant. So if we have a concealed container of gas molecules and we can see the gas molecules moving, if we decrease that volume, we can see that the number of collisions is going to increase with the sides of the container if we push that down on that lid to make the volume smaller. So that means that the more collisions with the sides of the container, the pressure of that is going to increase. So that tells us that volume and pressure have an inverse relationship. If volume goes down, pressure goes up, and vice versa. Volume increases, pressure decreases. So let's look at temperature and pressure. So if we take a sample of gas and we have it heated so that the molecules are moving faster, that means the temperature is increased. Now, that means the number of collisions with the sides of the container is also going to increase because they're moving faster. So that means pressure increases as well. So it shows us that temperature and pressure are a direct relationship. Now, if we look at number of molecules and pressure, we take the number of molecules and increase the number of molecules. Well, that's also going to increase the collisions with the sides of the container because there's more molecules. So that's going to increase the pressure. So that shows that number of molecules and pressure have a direct relationship. So let's look at the relationships for volume. So temperature and volume and number of molecules and volume. We already know that pressure and volume are an inverse relationship from what we saw with the pressure on the previous slide. So if we look at temperature and volume, if we increase that temperature, now this is assuming the pressure remains constant. If that lid is able to slide freely and we increase the temperature to keep the pressure the same, meaning the same number of collisions, it has to occupy a larger space. So that means the volume is also going to increase. So that is a direct relationship between temperature and volume. If we look at number of molecules and volume, and we increase the number of molecules in that container, if the volume remained the same, there'd be more collisions with the sides of the container, which means the pressure would increase. But because there's more molecules, we want the same pressure, that means it has to occupy a larger space to equalize those number of collisions, so the volume has to increase as well. And that shows the number of molecules has a direct relationship with volume. Now, there's one other one that we could have, number of molecules and temperature, and those really aren't related at all. So that's not something we're going to look at in this set of videos. So pressure has these three relationships. We have an inverse relationship with volume, direct with temperature, and number of molecules. And we know that from our volume, we had temperature and volume are a direct relationship, and number of molecules and volume are also a direct relationship. So you can see that there's only one that has an inverse relationship, that's pressure and volume. The rest of them have a direct relationship. Inverse, again, means that if one goes up, the other goes down. Direct means if one doubles, the other doubles, and vice versa. Of number of molecules and temperature, which we have no relationship, they're independent of each other. So let's look at the volume, temperature, and pressure relationships and see how we're going to derive our equation for the ideal gas law. So from what we talked about, we know that pressure is directly proportional to the temperature. It has an inverse relationship with volume, and it also has a direct relationship with the number of molecules. So we have this proportionality. We can combine all those proportionalities into one. Now, if we take a proportionality and we multiply it by a constant, that actually gives us an equality. So we're going to multiply that by the Boltzmann constant. Now what the Boltzmann constant is, if we take any pressure, volume, number of molecules, and temperature, and we put them in a container, that means we divide, multiply, divide. That's always going to give us the Boltzmann constant. And the Boltzmann constant is 1.38 times 10 to the negative 23 joules per Kelvin. And we can rearrange the Boltzmann constant equation and give us the first equation for ideal gas law, which is PV equals the number of molecules times the Boltzmann constant, and that temperature, remember, is the absolute temperature. So now let's define some other constants. So N naught is Avogadro's number, which you should have learned in a chemistry class. Avogadro's number is the number of molecules in 1 mole of a gas, which is 6.02 times 10 to the 23rd molecules per mole. Now, the number of molecules divided by Avogadro's number, capital N, gives us lowercase n, which is the number of moles of a substance. We can also take the Boltzmann constant multiplied by Avogadro's number. So we're multiplying two constants together, which is going to give us another constant, which is known as the universal gas constant. And that value is 8.31 joule per mole Kelvin. So we're going to use these two rules, rearrange them, and we're going to substitute into our ideal gas law equation. So if we rearrange that, N times N naught gives us the number of molecules. We can substitute moles times Avogadro's number in for capital N. We can rearrange the Boltzmann constant equation and get R divided by Avogadro's number and substitute that in for our KB constant. We can see that Avogadro's number is going to cancel out and give us that PV equals nRT. So this is the second version of the ideal gas law equation. So if we look at the two equations next to each other, we know that P is pressure, and that's measured in pascals. Pascal is a Newton per square meter. So that's using pressure in pascals. The volume has to be in cubic meters, so these are all SI units for physics. I know you probably use volume as a different unit in chemistry. Temperature has to be the absolute Kelvin temperature scale. N, lowercase n, is the number of moles. R is the universal gas constant, 8.31 joules per mole Kelvin. Then we know that N, capital N, is the number of molecules. The Boltzmann constant is 1.38 times 10 to the negative 23 joule per Kelvin. Now, we're going to also talk about the combined gas law. So we take a gas in one state, P1V1 equals nRT times T1. We have a second state where P2V2 equals nRT2. We can take those two equations and divide them by each other. So N and R, they're only things that are the same, so those can cancel out. And then if we rearrange this, we multiply P2V2 on each side and divide by T1 on each side. That gives us P1V1 over T1 equals P2V2 over T2. And this is known as the combined gas law. where P1, V1, and T1 are the pressure, volume, and absolute temperature of a concealed gas in one state, and the P2, V2, and T2 are the same number of moles for a gas in the same concealed container at a different state. Now, the reason it's the combined gas law is Jacques Charles, who was a French chemist, found that this relationship between volume and temperature between two containers where the pressure remains constant. This is known as Charles' law. Joseph Gay-Lussac, he developed this law of the relationship between pressure and temperature, which Boyle's law that relates pressure and volume. So this is named after Robert Boyle. He developed a relationship between pressure and volume 100 years or so before either Joseph or Jacques Charles came up with their law. But if we combine all of those into one law, that's the combined gas law. So that's why this equation is known as the combined gas law. So if we know pressure, volume, and temperature at one state, and we know pressure and volume at another, we can find the temperature, or if we knew the pressure and temperature, etc. So this is an introduction to the ideal gas law. I hope this is helpful, and I hope you have a great day and an even better tomorrow. If you found this video helpful, click the like button down below, subscribe to my channel, Cabby Coaches, and follow me on Instagram and X at Cabby Coaches.